Alright everyone, well this is one of my favorite examples in the lecture book. Here what we have is block P, which has a weight which is given to us, and we're told that the block is initially stationary when a force F begins acting on it, as shown in the graph below. The coefficients of static and kinetic friction in this problem are given to us, and we're asked to determine the speed of P at some later instant in time. So the way I'm going to do this is I'm going to note, because we're looking at speeds after some interval of time, we know this is going to be a linear impulse momentum equation, and so in that regard I'm going to start by drawing a free body diagram of the block. So if I do this, I'll have a normal force acting up from ground, we'll have the weight of the block acting down, I'll have the applied force F here, and I'll also have the force due to friction. Now if I go ahead and apply the linear impulse momentum principle on this system using the x direction, where x is classically defined as I did above, what I'll end up with here is that I'll have m times the initial speed of the block plus the integral over the time interval we want to look at here, and I'll just leave it written as indefinite for now, of f minus f dt is going to equal m times the final speed I want to recover, which I'll simply call v2. Now in this problem, if we go back up, we'll note that the block is initially stationary, and so we have initially zero speed, and so this term will go away. And so really what this leaves me with is trying to determine what this net impulse is here. So the way I'm going to do this is I'm going to note an important fact for you here, and that is that the friction force, little f, is a plot of the applied force, big F, is going to look something like this. We know the friction force is going to start at 0 as F is 0, and it eventually is going to peak out here at some value which we know is going to be equal to mu s times n. From that instant on, we know the system will start to move, and that value of the friction force will be given by mu kn. What this means is that the net impulse associated with the system will actually be 0 until we reach this F critical, that is that critical point where we break loose. That critical point will be determined by the maximum friction force we can have. So I'll note here that the maximum friction force we can have is going to be mu s times the normal force. If I go ahead and sum forces in the y direction on this system, I know the block's not leaving the surface, so I'd get simply that n is equal to w, which means that my maximum friction force I can have would simply be mu s times w. Now I don't often plug numbers into these problems, but let's go ahead and do it here because it's going to allow for complete analysis. So we're told in this problem that the static coefficient of friction is 0.5 and that the block weighs 100 pounds. This means that my maximum friction force I can have in this system is 50 pounds. If I use this knowledge, then I can come back up here to the top and say, well, when I break loose is going to be when F exceeds 50 pounds. When does F exceed 50 pounds? Well, because this is a straight line here, if I note that at 10 seconds we're at 200 pounds, that means that at 50 pounds I would be at, in this case, 2.5 seconds. What does this mean? Well, it means that I can split my impulse here and note that until I reach that critical time, 2.5 seconds, the impulse will balance each other out. That is, the applied force will balance friction. And so if I want to solve this problem now, if I take up here what I called equation 1 and express it, I know that that net impulse from time 0 to time 10 seconds can be rewritten as the impulse from 2.5 seconds to 10 seconds, the part which is unbalanced. The applied force in this case is a straight line. The slope of that line is given by, in this case, 20. So it's going to be 20 times t minus the friction force in that interval, which will be given by mu k times n. N, of course, is equal to simply the weight, so I'll have mu k times the weight. I'll integrate that over time and then set that equal to the final mass, which will be the weight of the block divided by the gravitational constant times the speed we call v2. Obviously, we know everything on the left-hand side here, as well as the mass of the block, so we can go ahead and solve this equation now and get v2. Obviously, a lot of complicated dynamics embedded in this problem, but once you go through it in a consistent manner, it's relatively straightforward. I'll leave it up to you to wrap this up. Best of luck. Take care.